So Isaac Newton certainly benefited from the work of René Descartes, but I'm not sure he really liked him. Regardless of that, we're going to look at a curve that goes back to the 17th century, something studied by René Descartes, amongst others. It's called the folium of Descartes, which I think actually is a Latin translation of flower of Descartes. That's because Descartes used to think that it did kind of a circle, a cloverleaf pattern in all these quadrants. In fact, it doesn't. But what we're going to be concerned with here is how do you find the derivative of this? Well, this is a little bit different than our work in previous sections. Why? Well, because you don't have y solved for. You don't have a function on one side and y on the other side. Y is kind of embroiled with everything else. And you can't, or in some cases it's very hard, but you can get y by itself. Yet we still want to find the slope of a tangent line, so we're going to need the derivative of functions like this. That's going to involve something called implicit differentiation. We'll come back and take a look at this one again in a little bit. But to start with, let's look at a much simpler problem. Problem number 2. We're going to do something called implicit differentiation. So this is section 3.5. Problem number 2 looks like this. X squared minus y squared equals 25. Does anyone recognize what the shape of this would be if you graphed it? Not quite a circle. It would be a circle if there was a plus there. This one's a hyperbola, right? Because you got a minus there. So regardless of that, it's a hyperbola. It has two branches that face away from each other. It's not a function, and we don't really have y solved for. Not that you couldn't solve for y2 without much effort, but we're not going to. Instead, we want to find the derivative here, but realize that y has some relationship to x. And when I differentiate this, I didn't mean to write a plus here, that's a minus. When I differentiate this, I have to regard y as some function of x. So I'm just going to put it in brackets like this to kind of really highlight it. Now, my goal is to find dy by dx. So I'm going to find the derivative here. And in the first case, that's not going to be a big deal. If I apply the derivative to x squared, what's the derivative of x squared? 2x. Good. But as I apply the derivative to y, things change a little bit. You have to regard this as something to differentiate using the chain rule. What's the derivative of the outside? 2 times y to the first power times the derivative of the inside. Well done. The derivative of the inside is dy dx. How about the derivative of the right-hand side? 0. Big goose egg. It's still a constant. Derivative of constant is 0. Our goal is to get dy by dx by itself. Now this 1 here, maybe I shouldn't have bothered to write that. That's just really 2y to the first power, or just 2y. I can add or subtract 2x from both sides. You get minus 2y dy dx equals negative 2x. Let's divide both sides by negative 2y. dy by dx equals negative 2x over negative 2y. Better yet, just x over y. So there's your derivative. dy by dx equals x over y. And this highlights and illustrates pretty well what you're going to have to do when you're working with these things. You're going to have to regard your variable y as some function, some unspecified function of x, and differentiate it using the chain rule, like we did up here. Derivative of the outside times the derivative of the inside. I probably shouldn't have written the 1 there because it looks like a derivative there. It looks like a prime. It's not. It's to the first power. Is there anything else I could say to help you out on this one? We okay with that first one? It's a nice little warm-up on this. Let's try problem number 4. Two x cubed plus 3y squared. You know what? I think I want to change it. 2x cubed. Let's do plus 3y to the 5th equals 64. We already did one with a square. Let's do something with a 5th power. So as you start these things, to help yourself out, everywhere you see a y, just kind of put it in brackets like this. And the reason I suggest that is to draw your attention to the fact that when you differentiate that term, you have to use the chain rule. You can't just say, okay, that's 15y to the 4th. That's not quite enough. So take a second and see if you can't find the derivative here. So apply the differential operator, d by dx, to all these terms. See what you can come up with. All right, is it chain? What'd you get when you differentiated this? I'm just looking for the derivative right here. So good, and that equals 0. All right, so well done. When you take the derivative here, it's the derivative of the outside times the derivative of the inside. Let's solve for dy by dx. dy by, let's see, it's going to be 15 y to the 4th dy by dx equals negative 6x squared. Divide both sides here. dy by dx equals negative 6x squared over 15 y to the 4th. And then put that in lowest terms from there. So divide out the 3, negative 2x squared over 5y to the 4th. Well done. Let's do a few more here. And they're going to get increasingly complicated. We'll start with, or we'll continue with problem number 6. Problem 6 looks like this. X squared y plus y squared x equals negative 2. Let's rewrite this as x squared times y plus y in brackets squared times x equals negative 2. What's one thing different about finding the derivative here? What extra care are you going to have to take in applying the derivative? Yeah, you have to use the product rule, all right, because you have a function times a function. So you're going to have to use the product rule. In fact, you're going to have to use the product rule twice. So, wow. Let's do this one together. But our goal is to differentiate with respect to x. So, let's see if we can't do that part without writing down f and g for all these things. Your first function here is going to be x squared, so the derivative is going to be 2x times y plus x squared times what? dy by dx. So we applied the product rule here. Let's apply the product rule here. Let's work on the derivative of the first part. What's the derivative of y squared going to equal? 2y dy by dx times x. That's the derivative of the first times the second. What's the derivative of the second times the first? 1 times y squared. All that's going to equal 0. So, all right, so we had to be a little bit careful here in finding the derivative because it required not only the product rule but the chain rule. Okay. Let's keep these on the left-hand side. These other two we're going to move to the right-hand side. Terms that don't involve my dy by dx, I'm going to move them out. So on the right-hand side, I'll get minus 2xy minus y squared. On the left-hand side, I'm going to factor out the dy by dx from both of these terms. So it's going to leave behind x squared plus 2xy times dy by dx. I hope I didn't do too much in one step here. So I did two things. Move these terms to the right-hand side where they change signs, and I factored out the dy by dx term from these two. What's the last thing I need to do to solve? Yeah, divide. So divide by x squared plus 2xy. Yay. Let's try problem number 24. You know, I don't see that there's really much we can do there. There's no greatest common factor here. I mean, you can factor out a negative if you wanted to, but it's not going to really change anything much. So, yeah, it's about as good as it gets on that one. So, yeah. Any other questions on that one? Now, implicit differentiation is going to be a big part of some of our later work when we start working with optimization problems, so related rates problems as well. So you're going to have to really get good at doing your implicit differentiation. It's not something that I would just kind of blow off and say, oh, it's just this one section. No, it's going to come up again. Problem 24. Now, I've written it a little differently on your handout, but it is problem number 24. I'm not sure that we really need it, but let me give you a quick reminder of how to work with something like this. Most of us would look at that and have no idea what the graph would look like. You can get a better idea if you kind of whip it into shape. X squared minus 4x plus y squared plus 6y equals negative 9. So I just move some terms around to get the x's and y's together. Let's complete the square on both of these things. So here and here. What number do I add here to get a complete square, a perfect square? 4. Remember, you take half of the middle number. Half of negative 4 is 2. Squared is 4. So I'll add 4 to both sides. Half of 6 is 3. 3 squared is 9. So on the left-hand side, I can rewrite this as x minus 2 quantity squared plus y plus 3 quantity squared equals 4. That looks a little bit better. Perhaps more recognizable as a circle. What's the center of that circle? Good. 2 and negative 3. And the radius? Good. Square root of 4 is 2. And isn't that special? That's right over here. Here's your circle. Now there's a couple ways you could find the derivative here. One of them, if you wanted to find dy dx, one thing you could do would be solve for y. So take this equation, move this to the other side, take the square root. You can't take the square root of this by saying, oh, square root of 4 minus square root of this. It doesn't work. You have to do the algebra here. It'll simplify like this. Move the 3 to the other side. Then you can find the derivative. Actually, you can differentiate right here because the derivative of 3 is 0. You have the derivative of the outside times the derivative of the inside. A lot of messing around. And you finally get down to this part right here after a lot of work. Yeah. Let's try finding the derivative implicitly. So here's the beginnings of that calculation. When I find the derivative here, I got to use the chain rule. So it's the derivative of the outside. What's that 1 represent? Derivative of the inside. So it's derivative of the outside times derivative of the inside. And the same thing here. Derivative of the outside times derivative of the inside. That's where I get the dy by dx term. Why don't you see if you can't finish solving for dy by dx? All right, you should have gotten something like this. Negative of x minus 2 over y plus 3. Now, how does that compare to our explicit derivative? Well, here's our explicit derivative. The difference is here we don't have anything for y, right? It's just all in terms of x. That's what we're used to. But if you take a look back here, right back up here, y plus 3 is equal to plus or minus the square root. If I replace this, then I get an equivalent expression. The difference is when I find the slope of the tangent line, here I need to know the value of y and the value of x. Here I just need to know the value of x. One's explicit, one's implicit. And that's the big difference in these types of differentiations. Are we okay with the calculations here? Let's remind ourselves of something about the derivative. What does the derivative measure? What does it tell you? Slope of the tangent line at any given point. Nice. Now, let's look at the form of the derivative here, the implicit form. Can you see that there's going to be a problem someplace? Where is there going to be a problem? Y equals negative 3, right? Let's look at the graph and see what kind of problem we're going to end up with at y equals negative 3. What's going on with the tangent line here and here? Vertical tangents, right? Vertical tangents have an undefined slope. Well, guess what? At negative 3, that slope's going to be undefined. Makes sense. Let's see if we can't make some more kind of hay out of this problem and look at x equal 2. What's the value of the derivative going to be at x equal 2? 0. At x equal 2, guess what? You got a horizontal tangent line here and a horizontal tangent line here. So, makes sense. These expressions, even though they start to look pretty crazy and you're doing lots of calculations to get them, they still represent the slope of the tangent line. In this case, 0, and in this case, undefined. but it's pretty clear the nice correlation between that slope of the tangent line and what's going on with the derivative here. So, nice example, very nice example. Any more follow-up on problem 24? Are we okay with 24? All right, so let's try some more here. Let's revisit the folium of Descartes. So let's go back to the other side of our handout. And we're going to see if we can't find the slope of the tangent line at this point. Now I'm also going to show you some tricks on your calculator so that you can calculate some of this stuff a little bit easier. So does anyone need to borrow one? All right. We're going to let a equal 1 in this, so that way the formula is a little bit easier. We're not going to mess around with that constant. There you go. So we've got x cubed plus y cubed minus 3xy equals, you know what? I think it's 6xy. I think they let a equal 2. Yeah, so let's make this. Yeah, let's let a equal 2. That way it matches the equation in the book. So something like this. To differentiate this, let's first rewrite this a little bit. Let's put the y's in nice big boxes, 6x and then y. What things are we going to have to take into consideration as we find the derivative of this function? Yeah, it's not very obvious, but right here you've got to use a product rule because you got a function times a function. Even though this is just a little old x, you still have to use the product rule in differentiating that. The first couple terms aren't too bad. 3x squared. Let's see. Sarah, how about the derivative of this one? What would that one be? Thank you. Times dy by dx. Minus 6. And then here I've got to use the product rule. Notice I'm just taking the constant and leaving it out front, but then we're going to apply the product rule. So it's going to be the derivative of the first times the second, plus the derivative of the second, dy by dx, times the first. Let's distribute this. So 3x squared plus 3y squared dy by dx minus 6y minus 6x dy by dx equals 0. Eventually I have to solve for dy by dx. So these terms I'm going to leave on the left-hand side. The other two terms are going to move to the right-hand side. I'm going to do two things here. Move these terms over and factor out the dy by dx term here. So it's going to be 3y squared minus 6x dy by dx. As these terms move to the right-hand side, their sign is going to change. So it's going to be 6y minus 3x squared. Divide both sides by dy by, or excuse me, the 3y squared minus 6y. Dy by dx equals 6y minus 3x squared over 3y squared minus 6x. It's not horrible to leave it like this, but keep in mind if we want to try and find the slope of the tangent line, or even like the equation of the tangent line at a point like 4/3 and 8/3 as given in the book and on our handout, then it's kind of a pain to have these extra coefficients lying around. I'd suggest you factor them out and cancel them. You can't just cancel 3 into the 6 here, 3 into the 6 here. You really need to factor out the 3 and do the cancellation. Let's just divide everything here by 3. 2y minus x squared over y squared minus 2x. So that's about as simple as you're going to get for the form of the derivative. There's your dy by dx. Now what's different about implicit differentiation is that in order to find the slope of the tangent line, I'm going to have to plug in not only values of x, but values for y, because the derivative depends on both of them. So here's where your calculator can come into play. Essentially what we want to do is we want to calculate this. Even on a calculator, this becomes kind of a pain. If you're doing it by hand, it becomes even more of a pain because you got to get common denominators, you've got complex fractions. Yuck. So let's try and be a little bit thoughtful about how we're going to do this. Let me make a little bit of a recommendation here for you. Let's take our value for x and store it in x. So take 4 divided by 3. And on the lower left-hand side, just above the on button, you'll see a button that allows you to store, right? Stow. So stow this in x. So stow, right there. Stow it in x. And then we're going to do the same thing for y. We're going to store a value in y. Now we're going to store 8/3, 8 divided by 3, and then store in y, except y really isn't as convenient as the x was just a moment ago. Does anyone see where y is on your calculator? Yeah, it's right above the 1. Now to get that, you're going to have to hit the alpha key and then the number 1. So there you go. Let's type in the expression here. And I'll be kind. Not everyone has all the fancy features of math type, so let's do it with parentheses, left parenthesis, and let's type in 2y. So that's 2 alpha 1 minus x, and then hit the square key, and then put a right parenthesis, divided by left parenthesis, alpha 1 squared minus 2x. And if you don't recognize the decimal that you get out of this, then hit the math key and then press enter twice. There you go, 4/5. Boy, a lot friendlier than squaring it out, getting common denominators, simplifying the complex fraction, lowest terms. Yeah, I don't know. What do you think? Give me some feedback on that. Is that, like that one a lot better? Okay. Didn't get 4/5? All right.
Can we store it for every letter?
Can you what? Yeah, you can store it in any letter, yeah. And it doesn't always have to be just numbers. You can actually store matrices on your calculator, although you have to store them in a slightly different place. So, yeah. Okay. Yeah. Yes, sir.
How do you clear one? Do you just store over it?
Yeah, you just store over it. Yeah. Just store over it. Now that you have the slope, you can actually find the equation of the tangent line. So the slope was 4/5. So the equation of the tangent line, let's see, had the points coordinate of 4/3 and 8/3, would be y minus 8/3 equals 4/5 times x minus 4/3. Oops. Rats. There we go. All right, I'm not going to go through and distribute and find it in slope-intercept form. Decimals can graph it from here, which is cool. All right, let's do logarithmic differentiation. Logarithmic differentiation is a really cool trick. I think you'll like this, and it can help you out when your problems get ugly. When you're looking at something that's looking pretty ugly, then maybe think about logarithmic differentiation. You can use logarithmic differentiation when your expressions are starting to look pretty nasty, but they'll simplify if you're to take logs. Yeah, just 1 second. Logarithmic differentiation. So an example of that would be problem number 68. Y equals the square root of x squared minus 1 over x squared plus 1, like that. The derivative here, if you were just to tackle it, would be a real pain. First, you'd have to use a chain rule. And when you differentiate the outside, which is your square root function, the derivative of the inside would require what rule? Quotient rule. Yeah. Listen to the enthusiasm in that crowd. Quotient rule. All right. There's no enthusiasm for it. So what else could we do? Well, let's do this. Let's take the natural log on both sides. And I'm going to write this as something to the 1/2 power. So it's going to be the natural log of x squared minus 1 over x squared plus 1 raised to the 1/2 power. The idea here with logarithmic differentiation is first to use as many properties of logs as you can. So I always think of this one as the parachute rule, right? The 1/2 can come out in front. So it's 1/2 ln of x squared minus 1 over x squared plus 1. Are there other rules, other properties of logarithms that I can use here? Quotient rule. So it's the ln of x squared minus 1 plus the ln of x squared plus 1. All right, that's still looking better. Let's go one more. I'm getting greedy here. Was it a minus? Yeah, minus, thank you. This term in here, x squared minus 1, that factors, right? How does x squared minus 1 factor? X plus 1, x minus 1. So x plus 1, x minus 1. So really this is the log of a product, which becomes the sum of the logs. ln of x plus 1 plus the ln of x minus 1 minus the ln of x squared plus 1. Okay, I think we've gotten as much mileage as we can out of the logarithm, right? We've used pretty much every property that we have over there on the right-hand side of the board. Remember what our goal was. Our goal is to find y prime. Our goal is to find dy by dx. So let's differentiate both sides here with respect to x. Now this is just like some of our work earlier. In here, what's hidden? You've got ln of y. And when you differentiate ln of y with respect to x, you have to use a chain rule. What's the chain rule going to say here? I'm going to get 1 over y times dy by dx. That's the hard part. The easier part is on the right-hand side. Let's differentiate a couple of these log terms. The derivative of ln of x plus 1, 1 over x plus 1, times the derivative of the inside. which is 1. So if you kind of forgot that, well, you get a pass in this one. All right. Plus 1 over x minus 1 times 1 again, which I'm not going to write. But the last one, we got to be a little bit more careful. What's the last one going to be when you differentiate it? Nice. It's 1 over x squared plus 1 times the derivative of x squared plus 1, which is your 2x. I still don't quite have dy by dx by itself yet. But it's not that hard to finish this up. To get dy by dx by itself, I'll multiply by y on both sides. Right? And yay, look. Dy by dx equals 1/2 times 1 over x plus 1 plus 1 over x minus 1 minus 2x over x squared plus 1 times y. Which isn't bad. But in order to get full credit on this problem, I'm going to ask you to do one thing. I want you to get rid of the y. How can I get rid of the y in this last expression? Well done. Yeah, just substitute in the original equation, right? Which was x squared minus 1, square root of x squared minus 1 over x squared plus 1. So there you go. You've got a nice explicit derivative. It doesn't depend on y anymore. It all depends on x. Yay. You want one more, or are you good on logarithmic differentiation? One more? I'll give you an easier one. Yeah. Let's take a look at problem 72. Now, a temptation on a problem like this would be to differentiate it as if it were a polynomial, as if you could just, multiply by the exponent and subtract 1 from the exponent. That doesn't work here. The reason it doesn't work here is because what you have in the exponent is not just a number. If it was a number, like 2 or 3 or 4 or pi or square root of 2, whatever it was, you could differentiate it as normal. But it's not. So let's apply logarithmic differentiation. So I get ln of y equals x minus 1 times the ln of x. Take the derivative on both sides. On the left-hand side, remember, your y here is special. Go ahead. 1 over y times dy by dx. Good. On the right-hand side, what rule do we have to use? Bryce? All right. It's all right. Product rule. All right. Good job. Product rule. So derivative of the first times second. So it's going to be 1 times ln of x plus the derivative of second times the first. So what's the derivative of ln of x? 1 over x times x minus 1. Let's clean that up just a little bit. If you distribute the 1 over x term, on the right-hand side, we'll end up with ln of x plus 1 minus 1 over x. So all I did was I distributed that 1 over x term. What comes next? Good. Multiply both sides by y. I get dy by dx equals the ln of x plus 1 minus 1 over x times y. But instead of y, we could write x times x, or x raised to the x minus 1 power. And that's it. Yes.
So would it also be possible to use the A to the U
Actually, the properties from A to the U, you could probably establish those really easily with logarithmic differentiation. But as far as differentiating with that one, with your using this property, derivative of A to the U equals ln of A times A to the U times du by dx. That one actually doesn't apply here. Can you see why? Why would that one not apply? Yeah, here in this formulation, A is a constant. Over here, you've got a function, a variable. So that one doesn't work. For homework, yeah, you guys thought you were getting out of here that early, easily? I don't think so. All right. Let's see. For homework, try 1 through 43, 57 through 61. We'll skip a bunch of problems, then 71 through 79, 81, not sure. Some of these are your logarithmic differentiation. So, I think like 65. Let's see. Yeah, actually, you know what? Part of this is in error. Let me fix that. You might. All right. Let me make your list even shorter. 1 through 33, 37, 45, 47, 53 through 57, and 65 through 75. So these are logarithmic differentiation. I'd practice those. Make sure that you understand those. It's a nice trick. If you have some trouble with it, please come see me or see Mimi. Have a great weekend. See ya.